Hi, today we're going to be looking at some of the source code that I'm using in my application GenFE8 that enables me to export to IFC format using the open source library from GeometryGym called GeometryGym.IFC. Now, the problem for me was that when I attempted to figure out how to export beams, columns, and floors from my 3D model to IFC correctly, because there's many different ways in the IFC libraries, and I'll talk about them in a minute and the challenges that they present. Now, before we get started, this is the software I'm working on called GenFE8. It's a structural analysis software, and it uses DevDept.Eyeshot as the 3D modeling component that you see here. So that's the .NET component that we use to render our model elements, and then on the left we've got a SpreadsheetGear component, which is pretty much a database of information that contains all the data that is driving the model, and the two are, bidirectionally linked to each other. Now, from GeometryGym, there's also a bunch of examples on how to create IFC files, and they really do help to get you started, but there's no example here on how to create extruded elements, especially when they are non-orthogonal, right? So if they're not vertical elements or plain horizontal elements, then it becomes quite tricky because as you might have experienced if you've tried this before, when setting up your, and we'll get back to the code here in a bit, but when setting up your beams, you need to be able, or framing elements at least, you need to be able to specify the vector, the direction. You need to create a profile along which you want to extrude that cross section. And if you don't get it all right with the correct reference placement points, then it simply just doesn't work. So I had a lot of trial and error runs until I finally found a solution that worked for me. And this is again related to the 3D control that I'm using, but the same principles might apply in whatever situation it is that you're working with. All right. Now, just to kind of explain how this is put together so it makes a bit more sense when we jump into the code. All of these elements here, such as this beam element, so if I selected this framing element here, this beam, it's currently extruded into 3D, and you can see it's kind of got a transparent sort of material applied to it. But if we look at the section that drives this, there's a section database with 2D cross-section shapes, and for the ones in this model I used rectangular shapes such as the ones that you see here on the screen. They are applied to elements, and if we switch off the extrusions here, they're applied to linear elements, and these are in fact horizontal and vertical, but there are some of them at different angles that are non-orthogonal. And yeah, so when we display them in the Eyeshot control, of course they all display perfect and the way we expect to see them. But when I exported them to IFC, I realized that there's a lot of things going wrong when I used the library, simply because I had no reference examples or anything to start from. So I'm going to talk you through and what I did to make this work. So I'll paste an example, or place an example of this code, this export function, in my IFC Exchange class somewhere for you to download, so it'll be in the comments. All I ask is that you just like the video, and that'll kind of help us to make more of these. Right, so once we've linked in the GeometryGym IFC DLL, we can start working on creating the project. So the first thing I did here was, of course, again in my case, using the Eyeshot control. I'm using units in my model, so I'm just checking whether it's meters or millimeters, because then I apply some multipliers in order to do unit conversions. I've created two lists here for materials and profiles. And profiles here, the IFC profile definition is the actual cross sections that we will use to extrude along those beams, but I'll explain a bit later on how we do that. Because we're not actually going to extrude them, we're actually going to rebuild the B-rep geometry, the 3D geometry, using the triangle faces from the solid geometry that we see here in the model. Okay, so the first thing to do is to create a new database. So this is what we've got here, and this is all in VB.NET. The same will apply in C#. So if you're more accustomed to C#, you can just use a converter to convert from VB.NET to C#. It's the same thing. The same principle. So, okay, so we create a new database. This is how we do it. It's a new database, IFC, and we use in my case, I use the IFC for design transfer format. So now that we've done that, we create a building. Again, I'm adding this to the database that we just created, and that name there is just IFC building. And then we're going to create the project, and again we are going to reference the building into that, and then say it's an IFC project, and here I've got my units as millimeters. Okay, the other code you see here is stuff that's got to do with my 3D model control, so don't worry too much about that. The first thing I do is I go through my spreadsheet data, so this input workbook, and I am looking for all the materials. In this case, I've only got one material here. And then on the sections, you'll see I've got a couple of sections. So what this does is first it'll go through the materials sheet, and it's going to then extract these properties. So we've got material name, we've got modulus of elasticity, we've got a Poisson ratio, and etc. etc. I probably didn't need to extract all of these since I'm only applying a couple. But then we create the materials. So I'm defining a new material. I'm assigning it to the database, which we set up here at the top. So we've got the database here. Then we are specifying the name, which is, the name of the material. In this case, it'll be rect 150 by 150 or shell 150 or whatever it is. And then we are assigning properties, or creating a new property element. So the IFC material properties has again got a name, and it's got the material that we created here assigned to it. I'm also creating mech properties. You probably won't need all of this in your applications, but I'll just talk you through it anyway. So with the mechanical properties, mechanical material properties, I can assign the Young's modulus and the Poisson ratio and the shear modulus. And what I do then is I add this to my list of materials that I've created here at the top. Right. I'm doing the same thing for the cross sections. However, it was probably not necessary to do this. I'm quite unsure myself. I'm not an expert in this, so forgive me if I've got some ambiguity in the code, but at least it does work and it gets me to where I want to be. I'm still recording all of the sections in any case, because you'll see later on we're going to assign them to materials, and I'll explain that in a bit. So we create a new cross section. Sorry, that's not it. That's a cross section from my model. Where we create the IFC cross section is here. It is a profile. It's called a profile. So it's the IFC arbitrary closed profile definition. And to do that, I need to extract some coordinates of points that creates that outer loop of the cross section profile. And if we go back here to the section library, we can see that is our profile, and each one of those curves will have vertices, and we're trying to extract those vertices and place them in a new list of IFC Cartesian points. So this is what I do here. I create new points and I add them to that list called outer points. Now that we've got this list, and here I'm just closing it because the start and the end node needs to be the same so that it's a closed polyline. So from that we create a polyline, so we use those outer points and we create a new IFC polyline. From the IFC polyline again, we can go ahead and create a profile, an IFC arbitrary closed profile. It's got the name and it's got the polyline assigned to it, and we add it to the list of IFC profiles. Right, so now we've got all the materials and all of the profiles in our project placed in lists, and they've all got names, so we can go and search them and index them later on. Okay, now one thing that I didn't realize is first, when I started working with the geometry, I thought, okay, so what I need to do is I need to find the correct profile, and then all I need to do is I need to extract that profile along the distance or the distance of the beam, right? So that should be quite easy. So when I go through my model entities, in this case you can see here I'm going through my DevDept.Eyeshot.entities. Oops, sorry, it's actually over here. Here I'm just classifying the variable. So here is my entities of type, and I'm saying that I'm looking for all the solids in my model. I'm also assigning custom entity data to elements, and I'm looking for those entities where the entity data is named frame data, right? And from that I extract some additional information like the length and the material name and the section name, etc. So here we can see that. So I'm defining a new variable here, the string material name, and we say it's xd.material, which is that frame data property, and we've got the section name. I'm also looking for the start and end coordinates or nodes for this particular beam element that we're working with, and then I am creating the IFC material, and I'm finding that from the list of materials that we created here earlier, and I'm doing that by using the name matching the name of the beam in question. The same happens for the profile. So I'm creating a new profile here, IFC profile dev, and I'm saying that we're going through that list of profiles and finding it by name. Now I'm creating two Cartesian points, the start point and the end point of my beam. So this is how we do it. We create a new Cartesian point for the start point. We reference the database, and then we've got the X, Y, Z coordinates there. Okay, and we do the same for the end point. Then we're going to create a start placement. Now the start placement is going to be the project base point. And this didn't make a lot of sense to me in the beginning. I thought the start placement is going to be the start point of the beam, right? So we need to create the start placement, the start point of the beam. But up here, you'll notice that I've created my project base point as a Cartesian point, which is at 0, 0, 0. I've created a project start placement point, which is this IFC access to placement 3D object. And we've got the project base point referenced in there, or assigned to it, and then we've got the project base placement. Sounds a little bit confusing, but this is the IFC local placement, and then again we have got this project start placement assigned to it again. So when we look at the elements in the model, let's say for example, and I'm just going to select a random beam here, let's say we're looking at this beam here. When we extract the cross section at the first face here of that element, it is already geographically coordinated, so it is already in that location, whatever it is. So it's already got those XYZ coordinates. All we need to do is to find the geometry, or to extrude it along the direction of the beam element at the specified distance, right? So if we go back here and we say that this placement has to be the start point, it's going to be incorrect, because it's actually going to double up on that, because that profile is already in that location, and that's where I made the mistake in my particular case. So that start placement is actually the project base point, because what I do now is I actually extract the B rep from the geometry. So these are solid entities, and all I do is I just convert that into a B rep, which is just a different type of solid geometry. And from there, I loop through the faces of the B rep, because what we're going to do is we're going to, instead of extruding the profile along the beam length axis, we are going to rebuild the faces. They already exist here in the model, so it's going to be a lot easier, because I can guarantee you the challenges that I faced in order to create that extrusion was pretty crazy. Before, I tried several things. So let's just say, let's just create a variable there, and we say we're going to create an IFC extrude area solid here. Now when we do this, and let me just say here new IFC extrude area solid, if we do this, we need to specify a profile. Now we've already got the profile because we saw that up here. We've got the profile, so that's all fine, but we also need to specify the depth. So that's quite easy because I've got the beam's length. So if I put in here profile and let's get the beam's length here, then we should be good to go, right? No, because if you do this, doesn't matter the orientation of the profile and whether it's already correct. In this case, it'll be rotated 90 degrees to the XY plane. It's always going to extrude it vertically unless you specify, and if we go here to the extrude area solid definition, unless you specify the proper direction and reference direction. So the only one that really works here, unless it's a vertical member, is if you go and if you look through these, you'll see we've got the profile, we need the position, we need the direction, and we also need the depth. But that also didn't work for me because I started calculating all of those vectors and positions, and I still ended up with objects in weird locations, unexpected locations. So eventually I got fed up with it and I thought, why is this so difficult? We've already got the 3D geometry here. Why can I not in some way or other convert the B-reps or the solid entities from the Eyeshot control into something that I can feed straight into the beam? Because the beam entities here has also got a shape function and it's got a IFC faceted B-rep entity that I can assign to it. So what I ended up doing instead was this loop. So after I've generated my B-rep entity, I loop through each of its faces. I create a new list of Cartesian points And then for each of those faces, I loop through the vertices and I add those. So I'm kind of reconstructing the faces. And so I'm creating those IFC Cartesian points. I'm just making sure here that they're in the correct order. And then once that's done, we create this IFC poly loop from those points from the faces. And then we create this IFC outer bound entity from the loop. And I've set that variable to true, which is the orientation. Whatever that does, I'm not sure. Don't ask me, but it works. And then finally, we create the new face. So we've got this new IFC face entity from this outer bound. And then I've got a list of IFC faces that I've set up or defined here that I'm adding this to. So once we've run through all of the faces in the element, and there aren't that many in this particular case, there's 6 of them, so it's not that much. So once that's done, we can go and create a closed shell from the faces. So we create this IFC closed shell entity and we assign that list of faces to it. Once it's done, we can go to the next step and create the B-rep, the IFC faceted B-rep, assigning the IFC closed shell to it. Once it's done, we create this thing called the shape rep entity, so IFC shape representation. We have assigned the B-rep to it and we tell it what the representation type is. In my case, I selected advanced B-rep. There's a whole bunch of different options here. I'm not sure which one is the correct one. I used advanced B-rep and it worked, so I'm happy with that. Now that that's done, we need to do one more thing here. So from the shape representation, we create the IFC product definition shape and we assign the shape rep into that. Now that we've got all of this information, I'm finally just creating a name for my beam entity. That is what's going to display in the IFC element. And I just produce an error if there's a duplication in the names, which should theoretically never occur in my case, but this is just a check in case that happens. Now, before I create the beam, I realized that I do want to check if it's a vertical element, because in that case, I'd rather create a column IFC entity. And if it's not, then it's a beam, so then it'll create an IFC beam entity, because in my software, we work with framing elements, so they're all of the type bar, which means we don't distinguish between columns and beams. But of course, when we send things to the likes of Revit and other packages that read IFC, we would probably want to distinguish them. So I'm just checking whether the X and for the start and the end are the same. And if it's both the same for the start and the end node, the X and the Y, then we know that we're working with a vertical element, which is going to be a column. So to create a column, we just go create a new IFC column. The building that we created earlier here when we defined our project setup is what we're referencing in here. And then we've got the placement, which is the coordinates of the start placement, right, which is the project base point. So this is very important. It's not actually the start point of the actual beam or column element, but it's that start placement, which is here. Start placement, sorry, where did I put that? Start placement, which is the project base point, which is at 0, 0, 0. And the reason for that is, again, because when we're extracting these vertices from the faces, they are already in the correct location. So we don't have to reallocate those positions. That'll just push it out further than what it's supposed to be. So that's why the placement is 0, 0, 0. Then we're assigning that IFC product definition shape to it, which is the B-rep assigned to it. I'm adding some properties here. So for the name, I'm using my beam name, and for the GUID, I'm not sure whether we have to regenerate the GUIDs or not, but I've got my own little tool where I just create new GUIDs, and I'll show you briefly what it looks like. It's just creating a new GUID. It's putting it to a string and it's adding it to a list here, and I'm just checking that it's not already been added to the list. They're supposed to be unique in all cases, but it's not always the case. So I'm just adding them to a list and making sure that the list doesn't already contain them. If it does, keep generating until they are 100% unique. So now that we've got the column entity, all we need to do is to create this thing called the column type. So there's an IFC column type. We reference the database there, the section name that we have defined here at the top. So that's the section name. And then we've got here the column type enumerator. So in this case, it's just IFC column type and it's column. There's a bunch of other options. I'm just using column. There's something called a material profile that we set up. So there's an IFC material. In this, we reference the section name, the material, and the profile. Remember, the profile is the one that we have referenced here from the list of IFC profiles. So we are actually creating our own BREP geometry, but we still need these profile informations here, and that's why I didn't remove it from my lists here at the top. So once we've got the profile reference in there, we can then go and create the material profile set. This is what it looks like, IFC material profile set, and we specify the section name and the material profile we've just created. Then we can go back to the column type, which we've set up here, and we assign the material profile set to its material select property. When that's done, we go to the column entity we initially created here, and we say the object type is the column type name. So this is a string value, so we want to get that string value there, which is the name, and that's how we assign them. Exactly the same happens for the beam entities, except they're not columns, they're just beams, but exactly the same workflow. For the floors that I'm adding, I'm following exactly the same principle. I've got regions that represents floors. So if I select this region here, oops, that shouldn't happen. But if I select that region there, that's what it looks like, or that's a solid entity. But if we remove the 3D, the extrusions here, and we just select that again, then we can see we've got a region there. So a planar region. So all I do is I get the region, I'm extruding it half of its thickness in one direction and another half in the other direction, so that it is centered on that region. I am going through the faces just like I did with the beams. I'm creating a list of points, I'm rebuilding the BREP, and I'm creating that closed shell entity. And all of this code I will provide for you. Again, it'll be in the discussion or in the notes, so you can get it from there. But anyway, let's see this in action. So if we now go and use the export tool to IFC here, and we'll just place this in this location here because it'll be easy for me to find that, and we'll just call this one YT example 01, and we'll save that out. So now that we're doing that, it's generating the geometry, and if we go to something like Navisworks, for example, and we append that into the model, we should see a successful model generated with those entities assigned. Now, I haven't addressed things like additional custom properties and metrics like volume and length and all of that, but I'm still working on it, so I'll get there in a bit. But you can see there is the model. If we select any entity here, it's in the list. We've got the IFC project there, we've got the building, and if I select an entity and we look at the properties here, we can see the type is IFC column, we've got the correct name, it's got its GUID, and some basic properties assigned to it from how we generated that from GeometryGym. So there's a lot more to create IFC models, of course, but this is hopefully enough to get you started, and hopefully it helps you save some time, because in my particular case, I had to do a lot of trial and error just to get to this point, and I'm hoping that it can help someone else. Okay, thanks. Talk soon. Bye.